Thank you everybody for coming out. This is a project that is near and dear to my heart. We did some really amazing work, and we're excited to share it with you guys today. There are some next steps at the end if you guys want to get involved. You can reach out to me at michael.berk@databricks.com or LinkedIn or whatever your method of contact is. But just setting the stage a little bit, we're looking to sort of give back, and this is a loaded term, but I'm just passionate about the oceans, passionate about helping the world. And we were fortunate enough to share a lot of the amazing resources at Databricks, both from an employee perspective and a compute perspective. And we're going to talk about that today. So, some background. As I have alluded to, my name is Michael. My background is in data science, and I worked at Tubi prior to this. Got some colleagues in the front. They're very nice and smart people. And I've been at Databricks for about 2 years. But my background is sort of ocean related. I studied environmental science, been scuba diving since I was a kid, a little bit of surfing, not very good. And yeah, just generally passionate about the oceans. And my colleague over here.
Hey everyone, I'm Patrick Leahey. I've been at Databricks about a year in the same role as Michael. My background is in data science as well as data engineering. I'm passionate about anything data. I've got some colleagues here as well from my past role, 8451, so thanks for coming. But yeah, so 8451's in Cincinnati. I have other passions, but Michael chose to put I'm passionate about Cincinnati. Also the environment, but yes, Cincinnati as well.
Yeah, he was out of office when we had to submit the slides, so that's on you. So, what is this initiative and how did it start? Well, a while back, we were tapped by this lovely man named Rob Reed. He works at Databricks, and he is head of the Databricks for Good initiative. And this initiative has 3 primary verticals. The first is education, the second is foreign aid, and then the third is the environment. And I was lucky enough to be appointed the project lead for the environment wing. What this is it's a pro bono initiative, so completely volunteer. Patrick worked many nights and weekends. I worked a couple as well. And we were just looking to give back and, again, make a difference in the world. The reason we chose oceans, completely arbitrary. I like the oceans, so I was fortunate enough to be able to steer towards that direction. So, what exactly did we do? Well, we treated this like a professional services engagement. We're both resident solutions architects. It's a post-sales role. It's typically very technical, and so we just treated this like any other job. We started off with scoping, then we went through the projects phase, and then finally, because this was pro bono, we had to do some marketing fluff like this talk. So, what is scoping? Well, with professional services, you have to determine what is the value add that we can provide. And sometimes customers know, sometimes they don't know, but typically we'll meet with leadership, specifically in the data space, and figure out what areas of expertise we can bring and how we can deliver an effective solution. It turns out the Ocean Cleanup, which is the amazing nonprofit that we partnered with, they actually knew exactly what they wanted. They really wanted to focus on reliability of pipelines. The reason is they don't have a very large team and they have a lot of contractors. So if stuff breaks, it's kind of difficult to bring in someone at 3 a.m. to come and fix that pipeline. So throughout this engagement, we focused on reliability and stability. We scoped 3 projects. The first was an architecture review, and this was just looking at their current ingestion framework. How could we make it better? They basically had no Databricks platform presence whatsoever. And so we were starting from a greenfield solution. The second was the RMS pipeline, which is the topic of this talk. And then the third is an ingestion framework that we didn't get very far on due to some legal blocking because it was handling sensitive data. We were looking to correlate financial funding with plastic removed from the ocean. And yeah, we got blocked pretty hard, unfortunately. And then finally, for the marketing fluff, we have a couple blogs. One is going out probably after Summit. One has already gone out. We have this talk right here that you're experiencing. And then we also got nominated for a Databricks for Good award, and we were in some amazing company within that award. So, what is the Ocean Cleanup? Well, their mission statement is to remove 90% of oceans floating plastic by 2040. And I'll let that sink in. That's a massive goal. They have a very impressive presence where they basically send out ships take nets at the mouths of rivers and collect a lot of plastic. And we were fortunate enough to contribute in a very small way.
Yeah, so I'm gonna take over here. I'm gonna talk through that second objective of the 3 that Michael talked about. So it's the RMS pipeline. I'll talk about what that means in terms of like non-technical details, and I think that's some interesting context, but then I'll kind of jump in and talk through some of the considerations that we had in that migration. Cool, so called it the RMS pipeline. So RMS stands for River Monitoring Systems. So these are systems comprised of cameras, other sensors, namely water level sensors, that are deployed on bridges throughout the world. The kind of goal here is to gather data that the team can use, specifically the rivers team at the Ocean Cleanup, to start to understand the overall trash footprint around the world. So you can see here in this diagram, it's cameras that are looking down at the river. They don't always have full coverage of the river, but this gives them enough to sort of start to get a picture of trash throughout the world. The reason they care about rivers is because a lot of trash that ends up in the ocean enters the waterway through the rivers, of course. So their goal, of course, is to have global coverage. It's not the case yet. This pipeline hopefully will be able to scale and support a global deployment. However, at this point, we're working with 12 deployments strategically placed on rivers that are known to produce a lot of trash into the ocean. Of course, they plan to have a lot more deployments, but they need to prove the value of it, and that's part of the goal here. So 62 cameras across these 12 deployments on a weekly basis, because images are taken in bursts every 15 minutes for each camera. It's about 130,000 images a week. So not a massive scale, but you can imagine as the organization would scale up, if they had shorter duration between image bursts or even live video, and a lot more cameras. This could be a whole lot of data. So we need to ensure that the pipeline is written well such that it can scale to meet that demand, but also is on a platform that can handle that. So they were interested in migrating to Databricks, and we were, of course, able to help them do that. And so I'll give a little bit more detail about what that data looks like. So this is a very high-level representation of a pipeline that's owned by a data engineering team at the Ocean Cleanup, so not the specific rivers team. Basically, just to demonstrate that there's a pipeline that basically when new data is collected, it is ushered into a Postgres database for the metadata, so things like coordinates of a camera, exact position of a camera, especially relative to other cameras, that camera's height above the water, as well as other information like water level data. This is all used in calculations and throughout the pipeline. However, there's also images that live in Azure Blob Storage. So this is essentially pretty high level. This is a diagram coming from the Ocean Cleanup, the rivers team, describing their overall pipeline. I'll just provide a quick summary here. Basically, this is a pipeline that pulls data from Azure Blob Storage, so image data, as well as metadata from Postgres, and does all this processing to understand, okay, do we see trash in these images? How much trash? Does a lot of filtering to ensure quality, does some tracking between images and bursts so that you don't count things multiple times, but you get different angles so you can really ensure that is trash. And outputs what they call vectors, which is just representations of these identified trash objects. And that goes to Postgres. So this is where we started. This is essentially the end-to-end the pipeline that we cared about. This central blue box with all these little black boxes in it, that's basically representing the pipeline. It was on Azure ML, and they had one of these for every single camera. So they had 62 pipelines. It's kind of already becoming a little unwieldy. That's just good context. We'll talk about how we were able to simplify that. But one key thing is each of these black boxes represents basically a pandas-based Python function. So there are obviously ways to scale that, but I'll talk through some of the considerations that we made to do so, but it's important detail. It's all pandas-based. So our core mission here was migrate to Databricks. We just need to get it over to Databricks. If we're able to make some improvements along the way, that'd be great. But really, we wanted to get them on Databricks so that they can unlock all the value from the platform and also consolidate on a single data platform. They're also using Dataiku. It's a little bit outside the scope of this specific talk, but we also migrated a pipeline from Dataiku to Databricks. So we consolidated some platforms. So in doing this migration, we had two main sort of considerations that we could bucket under trying to make this thing incremental, as well as distributed. So a reasoning for being incremental is, of course, if you reprocess images, that can really slow your pipeline down. It's kind of wasteful. It's not necessary. And so basically we want to process each image exactly once, though there's a few caveats there. We ended up doing something a little bit custom to ensure that that happened. But we needed to support some specific behaviors that the team required. Also, we wanted to make sure that we processed our images in a distributed way so that we could reduce complexity for the teams. They didn't have potentially thousands and tens of thousands of pipelines as they scale up, just to make things a little simpler for them. But also to ensure that we use our compute really efficiently, such that at that scale, they're nonprofits, so they want to be sure they're very intentional with their resources. So I'm going to jump into that first incremental type discussion. I do want to say if something isn't making sense, and I can probably tell if it's not making sense, I'll kind of pause and see if there's any questions, but do feel free to raise your hand. We have about 30 minutes left, so we can't take too many, but if something's not making sense, do stop me. Okay, so in discussing incrementality here, basically, like I said, that means we want to process each image exactly once. There's a little bit of nuance there. Like I said, there's some specific behaviors that we need to account for. So there could be cases in which we need to reprocess images, and also we needed to solve for being able to process only a subset of images for specific cameras, if that makes sense. So that adds a little bit of nuance, and it means that we can't just use structured streaming out of the box to do this. Okay, so solving for those, this is kind of the first technical piece of our pipeline that we built. So I kind of started with talking about what the pipeline looked like. I'm going to start talking about specifically what we built. So hopefully you can kind of see this and understand, but there's two Databricks tools that we used here. Well, more than two, but two specific ones that I'll call out and give brief descriptions for. Autoloader and change data feed, I'll call CDF. So autoloader basically guarantees exactly once data processing from cloud storage or object storage. Just out of the box, it handles everything behind the scenes, like checkpointing and everything. It's really great. And change data feed basically gives you change data capture on a Delta table so that you can understand what operations happened at different Delta commit versions in the past. So you can see if a record was updated, what a value was updated from, and two, you can see if record was inserted, deleted, et cetera. Allows you to process things downstream. So essentially here, we are ingesting all of our images and storing them in a Delta table, sort of. Why I say sort of is because we're actually not ingesting the actual content of the image for a couple of reasons. One, the Rivers team is adamant that they didn't want to duplicate storage and store all of the images at scale. That could be somewhat expensive. We did some simple math and it wasn't too much, but definitely can respect their kind of architecture there. And you'll see there's a line, maybe it's like line 8. Sorry, there's no line numbers, but dropping the content. So we're using the autoloader tool. You could probably think of a more efficient way to really do this because we are scanning all of the binary, like actual content of each image and then not doing anything with it. But this is a simple out-of-the-box way that we can use a Databricks tool to get quick value, ensure exactly once processing. Though you could probably reference like Azure Blob Storage metadata on a per image basis or something like that. But we use this tool and then we wrote to a table that has change data feed enabled. That's going to be important because our next step is going to need to be able to understand essentially when these images were read in. Okay. Also, the other reason why we didn't die on the hill of needing to actually store the data in the Delta table is because their code was already written to basically load the image from blob storage at time of processing. So if they needed to load it and do something with it, their code was already set up to pull that from blob storage, and they said that that was reliable enough that they could use that blob storage source as a bronze layer, essentially. So that's kind of what we went with. So this next piece is the custom state management solution that I came up with. There could definitely be better ways to do this. If you all know, I would be very interested. Obviously, the goal here is wanting to deliver the best solution. So this is what I came up with. If there are thoughts, happy to discuss afterwards. But basically, we had a custom state object that indicates for each camera the maximum Delta commit version that we've processed images up to. just a JSON object that we store in the mounted blob storage. But this, as opposed to just structured streaming, allows us to process subsets of data and reprocess subsets of data really easily, and do so in a way that, I mean, you could do it with structured streaming, but it would require some like manual or complex updating of like checkpoints and everything. So we thought that this would be a little more simpler approach, but obviously if there are, well, I guess part of the context here, we use that state to then create like a dynamic filter condition that we can apply to our, like all of the history for our CDF-enabled table to kind of suss out which images are set to be processed based on the cameras that are, like the camera serial values that are passed to the pipeline for processing in this specific execution, as well as an optional flag whether we need to reprocess certain cameras. So this basically accomplishes our goals, and it's pretty simple. We didn't want to make something super complicated. But anyway, if there are thoughts, I'm obviously open.
Yeah, and to elaborate a little bit, one of the key challenges with structured streaming is if you want to reprocess a subset of rows, there's no concept of row level lineage. So table A has row A and B, table B has row A and B as well, let's say. We don't know that row A and row A correspond to each other, and row B correspond to each other. So if we want to reprocess a subset of the rows at any point in our lineage, that's challenging, and so instead we just drop everything and reprocess from scratch. Patrick's solution allowed us to reprocess at the camera serial level. By having a flag, whether the camera was processed or not, we can sort of incrementally drop that flag and then reprocess based on that. So that was the big innovation.
Yeah, good synopsis, thank you. Cool, so I'll keep moving here. So here's some code that we used to do this. I didn't include the part where we're loading the JSON object, but basically we're creating using list comprehension to create a quick filter condition, and then we're applying that to a read of all history of the change data feed on that delta table that we read all of our image metadata into, so those image paths. Not super important here, but I mean, I think the general idea is probably the most interesting part. So what this gives us is this image metadata data frame containing metadata describing the actual images as they exist in blob storage that we can use to drive the rest of the process. So this is going to be data-driven, and all of our cameras, and you can't see it in this image, but all of our cameras would exist or have images in this same data frame for processing. So one of the requirements, we wanted to try to process everything in the same pipeline. Cool. So the second piece that we considered in this migration was ensuring that we were able to distribute all the processing. So, well, I'll kind of back up. And so we tried a lot of things here. Coming from like a data engineering background, I love Spark. Pandas is not really something that I love.
Who here likes pandas? Raise your hand. Who here prefers Spark? Raise your hand. Cool.
Yeah.
Thank
Honestly, it's a great framework, and there's tons of support for it. So there was some learning for me in this project. I kind of saw that even pandas-based solutions could scout really well on Databricks. Probably many of you know that and have kind of figured that out. But I'll kind of talk through my journey of kind of figuring that out and our final solution. So first thing I did was, all right, I'm going to rewrite this whole thing in PySpark using native Spark functions and everything. And I got about halfway through, but I was a math major, but this is a lot of pretty advanced like linear algebra and calculus and applying some deep learning models to generate inference. And it kind of scaled well, but it took me too much time. I probably spent too many weekends doing this. And so that wasn't going to be sustainable. I told Michael, I was like, I don't know that I can do this. So he's like, all right, let's brainstorm some other ways. And we were able to come up with some other solutions. So there are a lot of solutions. I'll talk about 3 here, but we can chat afterwards about some further things. So one kind of really cool solution is Ray on Spark. Who all here is familiar with Ray or used Ray? Cool, I'll call on y'all for some assistance. Anyway, so Ray on Spark is a GA product on Databricks now that happened a couple months ago. It's a distributed processing framework. However, how it distributes is slightly different than Spark, right? So Spark distributes like data partitions, and you process those in parallel. That's how it distributes. It can distribute across a cluster. Ray is kind of similar, but rather than essentially distributing by partitioning your data down, it does something they describe as kind of logical partitioning. So this is really cool because you can apply this to basically any Python code. So any Python function or class, you can do it statelessly or statefully. It allows you, basically, if you have any iterable, you can distribute that across a Spark cluster. So that's pretty awesome. We actually implemented a lot of this solution using Ray, but due to a couple factors, namely just lack of familiarity, I know a lot more about Spark, so that was where I wanted to go if I could. But it was a really cool solution, and we actually ended up using Ray for our migration of the data IQ piece. So super powerful. I'd encourage you to go learn about it if you have interest. But basically, as opposed to Spark, you can parallelize basically any Python code, and it's used in like very mature code bases, and it's just another complexity that I didn't quite have full understanding of. Though I was able to pretty quickly implement a pretty cool solution. So, because of that lack of familiarity, and because, as you saw, we had basically a Spark data frame that could drive our process, and it had basically some partition keys that we would be very interested in using to distribute our data, it kind of lent itself to a Spark-driven solution. So we had this pandas code, we had all these pandas-based Python functions that we needed to apply. And so we considered basically pandas UDFs, which you're probably somewhat familiar with, as well as pandas function APIs. Pandas UDFs has a couple types, pandas function APIs has a couple types, map in pandas, apply in pandas. And they have somewhat overlapping functionality. And in our case, the functionality was sort of that sliver in the Venn diagram. So we had a pandas data frame, a Spark data frame, group data, and we needed to be able to process subsets of that, so pandas data frames, and return pandas data frames from our functions. That's how the code was written. So we ended up going with pandas function APIs, specifically apply in pandas, because it's like a slightly higher level Spark API, so it could potentially benefit from slightly more optimization, but it's just something that kind of, you could pick either of these and do just fine. And they both vectorize Spark pandas, the data transformations using Apache Arrow in the same way. So cool options. So I said we ended up going with pandas function APIs, namely apply in pandas. So here's kind of what that looks like. So we had all those steps like image filtering, batch inference, et cetera. We were able to take basically the exact code that the Ocean Cleanup Rivers team had written. It was great code. It was well written, well commented. I mean, I was really surprised with the quality of this code, the unit tests and everything. So if we could avoid having to like change all that and just use this exactly how it was, we benefit from, they don't have to relearn their code, which I don't want them to have to do, but we don't have to reinvent the wheel here. So we're basically able to reuse a lot of their code and distribute it here. I have my grouping keys as camera serial and image burst ID because I think I mentioned we track a lot of their code. One of the specific tasks is tracking basically identified objects, like bounding boxes between images in a specific burst. And so those images need to be processed together. So we made sure they were by grouping by burst ID. Okay, so hopefully that makes a lot of sense. We can kind of come back with some questions, but kind of just going back through it, the end-to-end architecture looks something like this. It's a data-driven pipeline. We are able to process images incrementally, so exactly once by default, but support some specific behaviors without introducing a lot of complexity. And then we're able to distribute the actual application of the pandas-based code without a lot of rewrite. So it ended up being, if we kind of landed on this solution in the first place, this would have been a pretty quick migration, but unfortunately I had to do some learning, so that took a little while. But we finally came up with a pretty good solution that the team's gonna move forward with. Yeah, so that's basically end-to-end architecture there. I will hand it back over to Michael. We can take some questions now. We got about 15 minutes, or we can do them at the end.
I would just like to sort of provide some high level about pandas parallelization. If we look back at Databricks' history, it was sort of founded on the success of Spark. And for a while, there's a stereotype of it only being a Spark engine. Ray on Spark has opened up logical parallelism instead of data parallelism. So again, as Patrick alluded to, Spark operates by moving rows around and distributing that onto workers. With logical parallelism, you can basically execute any arbitrary piece of Python code. It might not be as performant in certain cases as Spark, but it's also a lot more performant in other cases. So with this, you now can use Databricks to run pretty much any piece of code. And if you're running Pandas specifically, there's a lot of great ways to parallelize, as we alluded to here. And then also one call out is Modin is a distributed library for Pandas. With Ray on Spark, it will use the Ray backend to actually run distributed Pandas in a multi-node fashion, not just a single node fashion. So if you got Pandas code, it can now run really fast on Databricks. And I guess could have for several years, but we got to play with this firsthand and it was really cool.
Yeah, and as part of our blog, we'll add some additional details about some additional methods, right? So there's a lot of ways to go about this. These are just a few, but we'll kind of talk through a more thorough analysis of the things we tried, things we didn't try, and why we didn't try them, et cetera. That could just be generally applicable. I've got some Pandas code. I want to distribute it on Databricks or under Spark environment. One quick thing I wanted to mention, and I can take some questions or kind of wrap up, but one kind of nuance that we found with trying to figure out Ray is just things I was learning. So you create an additional Ray cluster on top of a Spark cluster, and Ray does not operate on the JVM. So there's some additional complexities there. Obviously, Spark operates on the JVM. So trying to manage memory, if you have both like heavy Spark processing as well as Ray processing, that was a specific difficulty I ran into. Maybe you all know how to solve that in a more elegant way, but that was kind of interesting, I thought. Yeah. You want to wrap us up?
Cool, yeah. So I would like to present a couple more slides, and then there might be a minute or two for questions. But let's talk about the results. Just have a big, happy ending to all this, put a bow on it. So outcomes. As we mentioned before, we consolidated tooling. So they started with a Dataiku stack and an Azure ML stack, and then generally an Azure-based stack. And we were able to bring this down into Databricks. That was not the goal from the outset. We built everything with open source in mind. So Spark is open source. We relied heavily on MLflow. Ray on Spark is also open source. Ray is open source. And so we wanted to ensure that there was not vendor lock-in. We wanted to give them the capabilities based on the capital in Databricks employees' heads to then take the solutions and bring it wherever they wanted to take it. They decided to become a customer and are probably going to expand out on Databricks, but that was not the goal of the initiative. And then as Patrick alluded to, incremental processing, that was key for them. And then finally, they now do have the Databricks stack, and they're looking to build out a little bit more. So you're going to be bombarded with, like, what is Databricks? These are some of the cool things that we used. First is the Databricks SQL legacy dashboard. We needed to make a map. So we looked at the outputs of our forecasted amounts of trash, and we just simply plotted them by the region. The other thing, which I thought was really freaking cool, is we made a bunch of charts via the Databricks agent. So I just typed English, as if you were part of the keynote today, you would have saw. I basically said, hey, give me a bar chart that shows total plastic by deployment. And this is all that popped up. It didn't really take any iteration. So I don't know, it feels a little sci-fi. So those were both KPIs. We also need to look at descriptive stacks for monitoring. So in this case, we have water level. On the y-axis, we can see how many meters below the camera deployment it is. And this is really helpful to see, all right, is there a flood in the region? Is there not? Are our cameras still functioning? And just one call out is for, it looks like IC002, whatever that is. There was a big spike between October 1st and January 1st, 2023 to 2024. So these are the type of capabilities that you're now unlocking with Databricks because it's just a dashboard that plugs into a table. Also, outlier detection. We found an outlier. I don't know what happened, but now they can go and address this. It might be an issue with the code, it might be an issue with the camera, but it can be solved because it's been detected. And then finally, for next steps, as we sort of alluded to earlier, they are now in the Databricks stack so they can use Unity Catalog. This gives them lineage, permissions, governance, all that fancy stuff. It also gives them a lot of power. Like, I've built Databricks solutions for 2 years, and it works. Like, it has some weaknesses, but it's a pretty freaking powerful tool. And so with this tool, hopefully, if they build the right systems, it will scale out and allow them to impact the oceans more effectively. And then finally, as we alluded to, unification of tooling with Dataiku and Azure ML. Theoretically not in the picture. We don't want to speak to competes, but now they have a much more simpler offering. That said, it's not going to be easy. They have to build internal systems and internal policies that allow them to scale the system. They also have to migrate additional existing pipelines. And then finally, there is some employee education. Databricks is getting easier, but it's still not always the easiest. So, special shout out to Roberto and Andre, the lead data engineer and lead data scientist that we work with at the Ocean Cleanup, Renata and Martin for their leadership and oversight, and then also Brad Jarret, who's an RSA, and Bachar Wehbi, who is an SA. Both of them contributed to this as well. Thank you.
Thanks.